Today we're going to be covering limits with piecewise functions. And I know we've looked at these before a little bit in some of my previous videos, but I really feel like limits with piecewise functions are, you'll see them enough that I think it's worth dedicating a video specifically to them. So let's dive right in. We first need to go over a quick definition. So something called a juncture. And I don't know if this is an official definition or something that you might see in your textbook or if it's just something that I made up, but it's really useful. So a juncture is the x values where the function splits. So remember, you have your piecewise function and it splits at certain x values. Those x values are the junctures. Let me show you. Let's look at this quick example. So we have a function that is x minus 2 for x less than 3 and x squared for x greater than or equal to 3. So in this case, the juncture is x equals 3, right? Because you can see when you look at the function that that is where the function changes from x minus 2 to x squared. So that's where it splits. And a piecewise function can have multiple junctures, right? So let's look at this next one. Let's say we have a function that is x minus 2 for x less than 3, x squared for 3 less than or equal to x, and x less than 7, and then x over 2 for x greater than or equal to 7. So now this f of x has two junctures, right? The junctures are x equals 3 and x equals 7 because the function switches at both x equals 3 and x equals 7. So a piecewise function can have any number of junctures, just depending on how many splits there are. Now that we have that definition out of the way, let's actually look at piecewise limits. So there are two different kinds of limit problems that you might see with piecewise functions. The first is when you're solving the limit at a juncture. And the second, I bet you guessed this, is when you're finding the limit not at a juncture. And there are two different ways to solve these two kinds of problems. And we're going to look at not at a juncture first because that's a lot easier. So we're just going to knock that out real fast. Let's look at this example. We have the function f of x equals x over 2 plus 4 for x less than or equal to 1, and f of x equals 2x for x greater than 1. So x equals 1 is the juncture, and we're looking for the limit of f of x as x approaches 4. So we're looking for the limit as x approaches 4, and the juncture is 1. So we can immediately see here that we are solving the limit not at a juncture, right? And so now all we have to do is we just have to identify which segment of the piecewise function we're looking at, right? So okay, so we're looking for the limit as x approaches 4. So let's look at our piecewise function. Which does this fall into? Well, 4 is not less than or equal to 1. 4 is greater than 1. So that means that we're looking at that bottom segment, that 2x. And so all we have to do is find the limit as x approaches 4 of 2x. Because at this point, right, the function just equals 2x. And that's a really easy limit that we know how to solve. So the limit as x approaches 4 of f of x equals, we're just going to plug the 4 in, so 2 times 4, which equals 8. So all we did is we looked at this and we immediately identified that, all right, we're not finding the limit at a juncture. So which segment are we looking at? And okay, that's the bottom one. And then we just take the limit of that segment, pretending that's the whole function, right? Because at x equals 4, the function is 2x. So, well, 2x is a really easy limit to solve. We just plug in 4. That was how to solve piecewise limits not at a juncture. But now let's look at how to solve piecewise limits at a juncture. So we have f of x, and f of x equals x squared minus 1 for x less than or equal to 0. X plus 3 for 0 less than x, and x less than or equal to 1, and then 3x squared plus 1 for x greater than 1. So immediately looking at this, we know that the junctures are 0 and 1, right? Because the function changes at x equals 0 and x equals 1. And we're looking for the limit of f of x as x approaches 0. So immediately we know that we are solving this limit at a juncture, right? Limit is x approaches 0, and x equals 0 is one of our junctures. Okay, so how do we do this? Here, we have to look at the left-hand limit and the right-hand limit. So at x equals 0, f of x splits from x squared minus 1 to x plus 3, right? So those are the two functions that we're interested in here. The left-hand limit is the limit when the x's are less than a, in this case 0, and the right-hand limit is the limit when the x's are greater than a, and again, in this case 0. So we need to solve these two limits. So our left-hand limit is x squared minus 1, right? Because that's when x is less than 0. So we just plug that 0 right in there, and we get negative 1. Our right-hand limit is x plus 3, and so we just plug 0 in, and we get 3. And negative 1 does not equal 3. So since the left-hand limit and the right-hand limit aren't equal, that means that the limit does not exist, or DNE. DNE is it's a common way to write does not exist in calculus. And this is going to happen quite a bit. It seems almost like a trick question, and it's kind of annoying, but it's the way it is, right? You'll be asked to find a limit, and it turns out the limit doesn't exist. So just be forewarned that just because you're asked to solve a limit and you find that the limit doesn't exist, that's totally valid. Let's look at one more example of a piecewise limit at a juncture. So we have the same function as before, right? X squared minus 1 for x less than or equal to 0, x plus 3 for x greater than 0 and x less than or equal to 1, and 3x squared plus 1 for x greater than 1. So same junctures, x equals 0 and x equals 1, but now we're looking for the limit of f of x as x approaches 1. Before it was as x approaches 0, now it's 1. So again, we're at a juncture, right? Because we're looking for the limit as x approaches 1, and our function splits at 1. So what do? We have to look at the left-hand limit and the right-hand limit. And in this case, when the x's are less than 1, that's going to be our left-hand limit. And in this case, that is x plus 3. And when the x's are greater than 1, that's going to be our right-hand limit. In this case, it is 3x squared plus 1, right? Because 1 splits those two functions. So let's solve these two limits. Left-hand limit, x plus 3. We plug in 1, we get 1 plus 3, that's 4. So our left-hand limit is 4. Right-hand limit, 3x squared plus 1. We plug in 1, we get 3 times 1 squared plus 4, so that's 4. So in this case, the left-hand limit equals the right-hand limit. So we can say that the limit as x approaches 1 of f of x equals 4. So let's recap. Piecewise limits, right? You're either going to be solving the piecewise limits at a juncture or not at a juncture. If you're solving them at a juncture, you need to find the left-hand limit and the right-hand limit. And if the left-hand limit equals the right-hand limit, you're happy because that's your answer. And if left-hand limit does not equal the right-hand limit, you're kind of sad and the limit doesn't exist. If you're finding the limits not at a juncture, all you have to do is find the correct segment and solve it like a normal limit. And that is it. That is piecewise limits. If you found this video helpful, please like, subscribe, share it with your friends, and I will keep the math content coming.